I'd like to go over problem 2939. Now, in the Grob's textbook, they have you solve this in a way that is an approximation. And what I wanted to do is I wanted to talk a little bit about what that approximation is, how it breaks down, and why it breaks down, because I think that this will help give you a more complete understanding of how transistor biasing works, especially in the voltage divider case. Now, problem 2939 gives you a problem like this. The first thing I want to point out is that this is a PNP transistor. How do we know that? Well, the arrow's pointing this way, which means the diode is going this way. And if the diode arrow is pointing this way, this side's positive and this side's negative. So you got your P and your N. And then by construction, since it's a sandwich, this is PNP. Okay, that's how we know that. And they want to find out what VB is. You've got VCC applied as negative 20 volts. Put the V there. And you have two resistors, 6800 and 2200. Now, what all of you did on the homework and what the textbook recommends is you just did a voltage divider. You said that this is 0. And so the voltage here is going to be the ratio of this resistance to the total resistance times negative 20. In other words, you did 2200 over 2200 plus 6800, all of that times negative 20. And what you got was negative 4.8 repeating volts for VB. But I want to point out to you that this is an approximation, because what you did was you treated this as an unloaded voltage divider, meaning that all of the current flowing through this resistor flows through this resistor. However, there is a base current, and the base current is flowing this way for a PNP, which means that we'll call this I2, and this we'll call I1. I1 is not equal to I2. I1 is actually equal to I2 plus IB. Okay, that's just a statement of conservation of current. Now, if IB is really small compared to I2, then we can approximate I1 is approximately equal to I2. But that is an approximation, and it does break down depending on what resistor values you have. It works quite well in this problem, though, okay? Bear that in mind. So let's take a look at this problem in its full glory, and let's do it the quote-unquote correct way. So here we have the transistor circuit again, and I have the currents shown in red. Again, this is a PNP. We have 0 down here, and VCC necessarily has to be negative. Current is going to, conventional current, the flow of quote-unquote positive charges, is going to flow this way, it's going to flow this way, and it's going to flow this way. Okay, and we're starting from 0, and then we have negative. So rather than going from positive to negative, we're going from 0 to negative, but that's the correct direction. And we know that since current is flowing this way, this is going to be a voltage drop. So we're starting at 0, this is going to be some negative value. We know that when we cross this diode, the diode's pointing this way, it's going to drop by another 0.7, etc., okay? Now, what determines VB? What determines the voltage at this point? Well, there are several things. As we've already discussed, VB will be set by this voltage divider and our particular choice of R1 and R2. But VB also has to be equal to VE minus VBE. So this side and this side are pinned to each other. And if you think about it, what sets VE but the current flowing through this resistor, and that current is proportional to IB. So you have this sort of, it's not a circularity or feedback, but you have these two constraints that both have to be true in order to set VB. And so that's what we're going to use to ultimately solve for what VB is. So let's start with what we know about the currents. We know that the current through RE is equal to beta plus 1 times IB. And I'm being very pedantic here with that beta plus 1. Why is it beta plus 1? Well, IC is equal to beta IB, and IE has to provide current not only for IC, but also for the base. So IE is equal to beta IB plus IB, or beta plus 1 IB. IC, as we've said, is equal to beta IB. And I1, the current through resistor I1, is going to be equal to I2 plus IB. Now, let's also write what we know about the voltages. We know that V2, the voltage across this resistor, is going to be equal to VB, because it's just VB minus 0. And we know that V1, the voltage across resistor R1, is going to be the difference between VCC and VB. Okay? And lastly, we know that VB has to equal VE minus 0.7. Again, the diode is pointing this way, so the voltage drops by 0.7 when you cross this threshold. If we put these together, we can write a series of 3 equations. We have I2 R2, the current through R times its resistance, equals VB. We have that I2 plus IB, which is this current, times R1, is going to be equal to the voltage difference between VCC and VB. And then finally, we have that VE, which is beta plus 1 IBRE, minus 0.7 equals VB. So those are our 3 equations, and now we're going to put them together on the next page. I've written in the currents here, IE equals beta plus 1 IB. I2, I've rewritten equation 1 to be equal to VB divided by R2, and I1 is I2 plus B. So if we write equation 1, we get I2 equals VB over R2. If we write equation 2, we get VB is equal to VCC minus I1 R1, but we can rewrite I1 as being I2 plus IB. And then we can further substitute equation 1 for I2, and we get that VB is equal to VCC minus VB over R2 plus IB times R1. And now we're going to bring all of the VB terms over to one side of the equation, and we're going to solve for VB, and we get that VB is equal to VCC minus IB R1 divided by 1 plus R1 over R2. And if we multiply everything by R1 and R2, and we basically turn this into a fraction and then multiply by the reciprocal, what we get is VB is equal to R2 over R1 plus R2 VCC minus R1 times R2 over R1 plus R2 IB. I'm just simplifying this and breaking it into 2 terms. Okay, you can play around with the math on that. But I want to bring your attention to something pretty cool. You'll notice that this is the formula that you used to calculate VB, and it's just the unloaded voltage divider. Okay? And then there's this other term that you're subtracting out, this, which is just the parallel combination of R1 and R2 times IB. And you can see that if either IB is very tiny, or alternatively, if the parallel combination of R1 and R2 is very tiny, then this term becomes negligible, and VB is approximately equal to this. Okay? Now let's move on to equation 3. Remember, equation 3 is VB equals beta plus 1 IBRE minus VBE, the voltage drop across here. And since we have VB equals stuff and VB equals stuff, we're going to set this stuff equal to this stuff. And we get that B plus 1 IBRE minus VBE equals R2 over R1 plus R2 VCC minus R1 R2 over R1 plus R2 IB. And if we just do algebraic manipulation and solve for IB, we get this equation, which basically says that if you take the unloaded voltage divider voltage plus VBE and divide it by the parallel combination of R1 plus R2 plus beta plus 1 times RE, that gives you the current IB. Now, I've shown you how to do this the brute force way. I also want to show you a cool application of Thevenin's theorem. So we can do this using Thevenin's theorem in the following way. We can say that this circuit is equivalent to V Thevenin through R Thevenin of this part of the circuit, and then we can solve for V Thevenin and R Thevenin. So V Thevenin is just the voltage between this point and this point, which is just R2 over R1 plus R2 VCC. R Thevenin is what happens when you short VCC to ground, and R Thevenin, so if you're measuring the resistance across this point, if these are shorted to ground, is just the parallel combination of R1 and R2. So this circuit here can be turned into V Thevenin and R Thevenin applied to this transistor setup. It becomes like a base bias problem. And you'll notice that this is V Thevenin, and this is R Thevenin IB. So I'm not going to do the rest of the algebra, but using this schematic and these two values for V Thevenin and R Thevenin, you will get the same formula that I derived here, okay? So let's take this formula now and let's actually apply it. So here we go. Using the formula that we derived on the other page, we have that IB is equal to this term, which, as you recall, is equal to negative 4.888 volts repeating, plus VBE, which is negative 0.7 volts. This term, the parallel combination of R1 and R2, turns out to be 1,662.2 repeating ohms. And beta plus 1 RE is 201 times 1,000, which gives us 201,000. So IB is equal to negative 4.8 repeating plus negative 0.7 divided by the sum of these two terms, which gives us negative 5.5 divided by 202,662.2 repeating. And we get approximately 0.02 milliamps as our final answer. And you'll notice it's actually a negative sign, and that is because the base current is going this way rather than this way. And that is how you calculate the base current. So here is our circuit again, and we have, I forgot to write this in, but 1,000 ohms here. And we know that IB is equal to 2.067 times 10 to the minus fifth amps. And IE is going to be beta plus 1 IB, which is equal to 201 times 2.067 times 10 to the minus fifth. Okay. And that, as it turns out, is equal to 4.15, negative 4.15, or not negative, this is current, positive 1.45 milliamps, okay? And when we multiply it by the resistance to get VE, we find that VE is going to be equal to negative 4.15 volts, since it is a voltage drop. And now as we go across this way, it drops by another 0.7, so we get negative 4.85. And that is our actual VB. I'll remind you that when you just did the voltage divider, you got 4.88888, which honestly, pretty darn close. So again, the approximation happens to work for this problem, but it doesn't necessarily work always, okay? Now that we know that this is 4.85 volts, 4.85 volts divided by 2,200 ohms ends up giving us 2.205 milliamps, which will approximate as 2.21 milliamps. And 20 minus 4.85 divided by 6,800 gives us approximately 2.23 milliamps. And notice this is slightly higher than this, and it's higher by 0.02 milliamps, which is our base current. So everything works out. 0.2 milliamps plus 2.21 milliamps gives us 2.23 milliamps. This is 4.85 volts, which is consistent with the voltage drops across these. If I add the 0.7, I get to 4.15, which is all consistent. So this problem works out. So just to recap, when you did the simple unloaded voltage divider to calculate what the voltage at VB was, you got negative 4.888 volts. The actual VB is negative 4.85 volts. And so, this approximation was okay. But it only worked because IB was 0.02 milliamps, which is much smaller than I2, which was 2.2 milliamps. Depending on the resistor values, IB could be a similar magnitude to I2, and then you really have to use this hard formula, the one that we derived over here, the difficult formula, boom, okay? So this is the true formula for IB, and once you know IB, you can of course solve for VB, but in the problems given to you in GROBS, they expect you to just simply use the voltage divider approximation.